All right, guys, chapter 12, section 2, all about buoyancy. So we may have alluded to this already, but really in this section getting into, how if I have, let's say, like a chunk of steel and I drop it in a pond, it's going to drop to the bottom. Whereas if I have this giant, massive ship made of steel, it doesn't drop to the bottom and it's actually floating. So buoyancy really is the explanation behind why we can get certain objects to float. Before we get into that, though, just kind of a refresher on a couple of things. Mass and weight. So remember that mass and weight are not the same thing. Mass is how much matter is inside of an object, and weight has to do with gravity. Mass has nothing to do with gravity. So if you have a mass of 50 kilograms on Earth, you're going to have the exact same mass on Mars, 50 kilograms. Your weight, on the other hand, because weight is a force caused by gravity, it is going to change if you go somewhere else and your gravity is different. So on Earth, let's say your weight was 110 pounds. If you went to Mars, your weight would only be 42 pounds. How can that be? You're still you. Everything's inside of you the same. Yes, your mass stays the same. Your weight is different. So what does that tell you about the gravity on Mars? Do you think the gravity on Mars is less or greater? It's less than, right? Because it has less weight. It means there's less of a pull for you on the planet Mars. So mass, how much matter is inside, weight, force caused by Earth's gravity. Gravity has to do with weight, whereas mass does not. Buoyancy has to do with fluids. So fluids are a form of matter that flow when a force is applied. I think often when we think of fluids, we think of liquids. And yes, liquids are fluids, but they are not the only fluid because gases are also fluids. So gases are also matter that flows when a force is applied. So both liquids and gases are fluids. So important thing again, saying what a fluid is, it flows when a force is applied. So buoyancy is the measure of the upward force that a fluid exerts on an object that it's submerged in. So buoyancy is really kind of easy. Most of us have gone swimming, especially up here in northern Minnesota, going in the lake, even if it's the pool at the high school here. If you are floating, we all know that water is pushing up on you, right? You notice how it's a lot easier to kind of move around in the water. And that's because that water has a force pushing up on you. That force pushing up is the buoyant force. So when something is in a fluid, that fluid pushes back on that object. And that push back on the object is buoyancy. So we use water a lot. We use that as an example because a lot of things float in water, but keep in mind that gases are also fluids. So when you talk about something floating in air, we'll put in quotes, like if you have a balloon that's floating in air, the air that's surrounding the balloon is also exerting an upward force on that balloon if it is floating, and that would also be the buoyant force. So important to notice in these pictures here, if you look at the boy swimming, the buoyant force would be going in the upward direction, whereas his weight would be pulling down towards Earth. Same thing with the ball in the pool there, the beach ball, whereas the weight is pushing the ball down, the buoyant force is pushing up. So remember, buoyant force pushing up, weight's going to be pulling down. What the buoyant force is determined by the volume of the object that is underwater. So the more that is underwater, the stronger the buoyant force is going to be pushing up on it. So they show you that with the beach ball there. As you push the ball down, there is a stronger buoyant force pushing up on that beach ball. And if anyone has ever done that before, actually pushed a beach ball underwater, you know that it is a much stronger force pushing back up on that beach ball. So something kind of cool is the Archimedes principle, and your video assignment that you guys are going to do this week has to do with this, so I'm not going to go into too great a detail. But there was a famous scientist a long time ago that discovered this really interesting fact, and it is now since known as Archimedes' principle. Obviously, he's the one that discovered it, named after him. So what Archimedes discovered was the buoyant force is equal to the weight of the fluid displaced by the object. I'll say that again. The buoyant force is equal to the weight of the fluid displaced by an object. The whole story with Archimedes revolves around him being in a bathtub, and it's kind of a funny story. Like I said, you'll get into the video here, but when you submerge something in a fluid, there is a relationship based on your weight and how much water you're pushing aside. So if we look at the picture on the left-hand side here, we have a rock. and it looks like it has a weight of 29.4 newtons. That's what its weight is. It's on the scale there. Remember, newtons is the measurement that we're using for weight. So it's 29.4 newtons. If I take that same rock and I put it in water, it's going to push aside because the volume of that water, or volume of the rock, happens to be 1,000 cubic centimeters. That's the amount of water it's going to displace. So 1,000 cubic centimeters of water. 1,000 cubic centimeters of water has a weight of 9.8 newtons. So what that means is 9.8 newtons is the force pushing up on the rock. So the buoyant force is equal to the weight of the fluid displaced by an object. So because that rock displaced 1,000 cubic centimeters of water, and 1,000 cubic centimeters of water has a buoyant force or a weight of 9.8 newtons, that's the force pushing back up on it. So when you think about that, if the rock weighs 29.4 newtons and 9.8 newtons is pushing up on it, which force is greater? 29.4 or 9.8? 29.4, hence the reason why the rock sinks. So it's kind of a weird principle because we don't deal with it very frequently, but really that's all it's saying. So the buoyant force is equal to the weight of the fluid displaced by the object. So if you think about it, if that rock could somehow displace more water, couldn't you increase the buoyant force? So it's really hard to change the shape of a rock, but if we think about changing the shape of other things, so let's say that steel that we talked about earlier on, instead of having a steel cube, now let's take that steel and spread it out over a greater area in the water and make it displace more water. As soon as you make it displace more water and push aside more water, you're going to be increasing the buoyant force acting on the steel. As soon as it's more than the weight of the steel, then you're going to get it to float. So sinking and floating has to do with buoyancy. I think we often think about it has to do with just density. No, it has to also do with buoyancy. So buoyancy explains why some objects float and why some objects sink. The object's going to float if the buoyant force is greater than the weight. So think about that. The buoyant force pushing up, if it's greater than the weight of the object, it's going to float. It's going to sink if that buoyant force is less than the weight, just like we saw with the rock in the previous picture there. So the book shows you this picture here. We have a foam block that's 100 grams. And because it is not very dense, it has a low density, only 100 cubic centimeters of the block ends up being submerged in the water. Whereas the wood block, because it's heavier, it's more dense, it's going to push aside 300 cubic centimeters of water. So you can see the difference in floating there. So just think about this. Which force is bigger? If the buoyant force pushing up is bigger, it's going to float. The buoyant force is not bigger, it's going to sink. So density and buoyancy. So the average density, as we've learned about already, is the total mass divided by the total volume. So objects with an average density greater than the density of water are going to sink. Objects with their average density less than the density of water are going to float. So here's a picture. We have two balls. They're the exact same size. So you have a 5 centimeter steel ball. Its total average density is 7.8 grams per milliliter. And then the wood ball is 0.75 grams per milliliter. So the density, 1 gram per milliliter of water, because all water is 1 gram per milliliter for density. The wood ball is going to float because it's less than 1. The steel ball is going to sink because it's greater than 1. So even though the buoyant force is the same, their weight is different. So because the weight of the steel ball is more, it's got a higher density, it's going to sink. So boats and average density. So to make steel float, you have to reduce the average density by increasing its volume because you're not going to be changing its mass. So if you look at the picture here, the mass stays the same. If I want to change the density of it, of the actual box, I need to make it bigger. I need to increase its volume. And ships do this by taking the hull of it and adding air to it, essentially, making it wide on the bottom, so you're pushing more water aside and then filling it up with air. So to make steel float, you reduce the average density by increasing its volume. You're pushing more water aside. So overall, in this lecture, so remember fluids are anything that flows when a force is applied. So both liquids and gases are fluids. Buoyancy, the measure of the upward force that a fluid exerts on an object. And then Archimedes' principle, the buoyant force is equal to the weight of the fluid displaced by an object. Objects are going to float if their buoyant force is greater than their weight. They're going to sink if their buoyant force is less than their weight.